I just want to do a very quick review of lines and planes, so we're all at the same pace here. So just remember that if we want to find the parametric equation of a line that passes through a point and is in the direction of a particular vector, I know how to do that. Those are going to be all the points. So if this is P0, let's say, it's going to be all the points in vector form that are given by P0 plus T times V. That is the vector form. And if I write that in coordinates, that is going to be its X, Y, and Z given by the point 1, 0, 2 plus T times the coordinates of the vector. So minus 1, T times 1, T times 1. So those are just 1 minus T, T, 2 plus T. So that is the parametric equation for that line. Okay, so this is the parametric equation for the line is given by this expression. Now, if I want to find a segment that goes from one point to another, so what I have now is 2 points in somewhere in space. Here, there's a point P and a point Q. And what I'm going to do is, first of all, I'm going to find the vector from P to Q. Then I'm going to write the line that goes through P with that vector. And then I'm going to figure out where I should cut off so that I am literally going from P to Q. There is, though, a parametric form or a form for that. Such a segment is 1 minus T times P plus T times Q. So those are all the points in that segment. You can see that if I plug in T equals 0 in this expression, oh, I meant to say for T between 0 and 1. Let's see if that works. You see that, well, this is going to be a line, and this is at 0. This is 1 times P plus 0 times Q. So at 0, we are at P. And by 1, at 1, this is 0, and I get Q. So by once the parameter is at 1, I'm actually going to be at Q. Okay? So I can actually just use this equation. So this is going to be 1 minus T times 1, 2, 3 plus T times 1, 0, 1. So in parametric form, it is going to be X is 1 minus T times 1 plus T. Y is 1 minus T times 2 plus 0 times T. And Z is 1 minus T times 3 plus 1 times T. So those are, I can simplify this. 1 minus T plus T is actually just 1. Y is, this is going to be 2 minus 2T. And this is going to be 3 minus 3T plus a T. I think this is 3 minus 2T. Yes? If I am correct, then this is so this is for T between 0 and 1. And if I am correct, the vector, the direction vector for this line, this is a line, but then the parameter is restricted, so it's just one segment, but it's a piece of a line. The vector that appears here is 1 minus 2 minus 0, 0 minus 2 minus 2. So the direction vector seems to be 0 minus 2 minus 2. It should be also, it should correspond to difference between this vector and this vector. And if I do that, 1 minus 1 is 0, 0 minus 2 is minus 2, and 1 minus 3 is minus 2. So that is the correct direction vector. You can see that at 0, when I plug in T equals 0, I get the point 1, 2, 3. So I am at 1, 2, 3. And you plug in T equals 1, you should get Q. So this is the correct answer right here is the parametric equation for that segment. Right. Now, to show that two lines intersect and to find the point of intersection, we write these in parametric form. So L1 was given by x is minus 2 plus t, y is 2 minus 2t, z is minus 1 plus 3t. And if they are going to coincide for some parameter s, they have to be exactly at the same point. So you set it up equal to minus 2 minus s, 1 plus s, and minus 2s. And then you just go from there. So now this is a system of equations with two parameters, and you have to try to solve it. You can use one equation here, say, to solve t in terms of s, plug in here and get a value for s, then plug back in, you get a value for t. And then the last step, crucial, is to check those values that they satisfy this last equation. If they do satisfy it, that's a point of intersection. If they do not satisfy this line, then they're not a point of intersection. Okay, so you can, we'll leave this for you to finish up, but I think this is exactly the same example I did in the video. So you can, in the previous video, so you can look at it there. The one, somebody wrote to me, thank you, I don't know who you are if you're here, that I made a mistake in the previous video, so let me fix that. I was trying to investigate the relative position of these two lines. Two lines in space, they can be exactly the same line, they can be parallel, they can be intersecting, or they can be askew, okay, which is not parallel and not intersecting. Much of that depends on what the vectors are like. If the vectors are parallel, then they can be parallel or identical. And if their vectors are not parallel, then they can be intersecting or skew. So let's see what the vectors are. So the vector for this one, you look at, this is a parametric form. So you look at the coefficients in t, and this vector is 1, minus 2, 3. Right? And then the vector for this one is 1, minus 2, 3. It's actually the very same vector. Didn't get very creative there. It could have been that this is a multiple of this, but in this case, it's exactly the same direction vector. So these are definitely at least parallel, but they could be identical. Okay? So we want to figure out if they are parallel or identical. How do we know that? If they share one point and they share the same direction vector, they will be identical. And this is where I made a mistake, which is that I found one point in L1, and I found it wrong. So, so a point on L1 at t equals 0, and I believe I said it's 1 minus 2 minus 1. But if you see, when t is 0, this whole coordinate goes to 0. So it should be that I get the point 1, 0, minus 1. And now I want to check if this point is on L2. Is P on L2? How do I know that? Well, I have the coordinates for x, y, and z in parametric form for L2. Those are 2 plus t. This t is slightly a different parameter. It doesn't have to be exactly the same parameter. So it doesn't have to be t equals 0. It could be for other parameter, for other value of the parameter that I get that. So here I get minus 2t and 2 plus 3t. And this has to be 1, 0, minus 1. So let's see. From this equation, I get that t is how much? Negative 2 plus t has to be 1, negative 1, right? All right. Does that satisfy the other one? So what happens in here, if I plug in t equals minus 1, I get minus 2 times minus 1, and that is minus 2 plus 2. That is 0, And in here, when I plug in t equals -1, I get 2 plus 3 times -1. That is 2 minus 3 is -1, so it works. So it is. So these are identical. So L1 is actually equal to L2. They're not different lines. Okay? You can see that you can investigate the positions just by knowing some points on the line, the vector, the direction vector for the line. You can figure all that out like that. Now onto planes. Remember that a plane, we describe planes by, you can give me 3 points on the plane, but eventually what I want to describe them is by 1 point on the plane, let's say P0, and one normal vector, one vector that is perpendicular to the plane. And once I have those two pieces of information, then there is several ways of expressing this plane, but the most usual ways are what we call the scalar form. So the scalar form is, it comes from the scalar product, that's where the name comes from, which is the dot product. So we want, it was something like r minus r0 dot n is 0, which in this case is the vector x minus the position vector for P0 dot with n, 1 minus 1, 2 has to be 0, so they're perpendicular. And that gives me 1 times x minus 1 minus 1 times y minus 2 plus twice z minus 3 is equal to 0. This is what we call the scalar form. And I can do also a what we call the linear form by simplifying all of this. So this is x minus 1 minus y plus 2. Be careful with distributing signs. Plus 2z minus 6 is equal to 0. And I get x minus y plus 2z. And that is minus 1 and 2 is 1. And minus 6 is minus 5. So I can write it as like this if I want to. Like that. And you can check just for sanity, the point, the original point has to be here. So plug in 1, 2, 3. 1 minus 2 is minus 1. And 6 minus 1 is 5. Minus 5, I get 0. So that point is on the plane. And the coefficients in x, y, and z have to be the coefficients of your normal vector. And that's a 1, a minus 1, and a 2. So that is normal. It is a plane that is normal to this vector, and it goes through that point. So that plane is correct. Yes?
Would you rather use the scalar or the linear equation?
That's a great question, because I don't know anyone that has ever written planes in this form, in scalar form. You always want them, at the end of the day, you work with them in linear form. But some of the assignments might ask, can you write it in a scalar form? The scalar form is just interesting. It just gives you right away a point that it goes through. It tells me right away that it goes through the point 1, 2, 3. And it tells me right away that it's normal to 1 minus 1, 2. So it's giving you those pieces of information in the same line, while in here it's not clear at first, like what's a point on that plane? Okay? We've sort of forgotten the point in the last form. It's there, but you have to, now I have infinitely many points to choose from. Now, if we want to find the equation of a plane that goes through 3 points, then I have P, I have Q, and I have R. And then what we do is, first of all, I can figure out what PQ is and what PR is. Remember, those are the coordinates of Q minus the coordinates of P, and the coordinates of R minus the coordinates of P. and that will be q minus p, that will be 0, minus 2, and 1 minus 3 is minus 2. And PR is the coordinates of R, so minus 1, minus 1, 0. And now what I need is a normal vector, and that's what the cross product is for. So my normal vector, I'm going to pick PQ cross PR. So, and remember that to find that vector n, I do the cross product. So I would have to find the determinant of, I put here the coordinates of PQ, and then the coordinates of PR, and whatever this is the normal vector. And then you use the normal vector and the point P, for example, to find the plane. Did I make a mistake? Some people are. So R minus 1 is minus 1, minus 1 minus 2 is minus 3, and 1 minus 3 is minus 2. Is that right? Thank you. Right, so once you have that, then this is going to be some vector ABC, and then you're going to write A times X minus the P coordinate. So the coordinates of the point P, for example, and that is going to be the equation for the plane we're looking for. So are the planes given by those equations, are they skew, if that's a thing? Are they parallel? Are they identical? Are they intersecting? Or I'm lost in space. All right, finally, parallel has overpassed. I'm lost in space. So let me say something about this. First of all, there is no such thing as skew planes. If you think about two planes, they can be identical, they can be parallel in space, or if they are not parallel, they will intersect at some point. So there is no, the concept of skew is for lines where you can have two lines that are not parallel, like such as the x-axis and a line that is parallel to the z-axis but not the c-axis. Those are probably going to be skew lines, and those are never going to touch, okay? And they're not parallel. But for planes, if they are not parallel, then just think about the planes at some angle, then they will connect at some point, okay? So skew is not an option for planes. Now, are they parallel? Are they identical? Or are they intersecting? We need to know about their normal vectors, first of all, and then that will tell us. If the normal vectors are not parallel, then they will intersect. If the normal vectors are parallel, then I have to do some math to see if those planes are exactly the same. So let me do that. I think I have to exit this and then go back to this. So I have to first look at this. One is in scalar form, one is in linear form. Do these two talk to each other? A little bit, because I can actually figure out from this one, I can already figure out what the vector is. The coefficients in front of those quantities are the coefficients of my normal vector, and the coefficients in here are the coefficients of a normal vector. So this one is 2 minus 4 minus 2, and the normal vector for this one is 1. Maybe I should call them normal. Should call them by n, because they're normal. And then for this one is 1 minus 2 minus 1, which are multiples of each other. So n2 or n1 is twice n2. So this tells me they are going to be either parallel or identical planes. And now how do I know? I can figure out that by computing exactly what the equation is for this one. That is 2x minus 4 minus 4y minus 4 minus 2z plus 2 is equal to 0, and that is 2x minus 4y minus 2z, and then minus 4 and minus 4 is minus 8, plus 2 is minus 6, so this will be 6. And if I divide by 2 every coefficient, which I can do, this is x minus 2y minus z equals to 3, which is exactly the same as we had here. So they are identical. Okay, so to compare planes, relative positions of planes, you need the normal vectors first, and then go from there.